All right. So as we talked last time we went over the midterm exam, and there was a question about problem 2.4, and yes, it was misgraded. The rubric I gave the TAs said to take a half point off for float, and the TA who graded that problem, I guess in the moment misread it and said take a half point off for integer. So floating point answers got full credit, integer answers got a half point off. That's been corrected, so your score may have changed. Yeah, so that's one of the nice things about that software for your exams is that you can change one place and it detects the other ones that were the same. And so they all were changed accordingly. Oh, come on. There we go. So I finished Lab 1 regrades. I finally got around to it. I know Lab 2 and Lab 3 regrades. I'll get to those maybe not this weekend, but I hope I will. You don't have to do anything. As we talked about these, some of you had ill-formed files. Those are the ones I'm going back to correct. I had originally asked you to tell me why it wouldn't load, but that's turned out to be much more cumbersome than just letting me manually correct them. The problem is it's a little time consuming, so I have to have an hour or so to sit down and look through each one of the files. So the way I do this is I find the function that has the syntax error and I just comment it out. So you get no credit for the function that's flawed, but at least the other functions will be graded. All right, question day 7. A lot of you had struggled a bit with this, so we'll look at it today. Question day 8 will be out this afternoon or later this morning. I provided a list or a handout with, I think, 20 or 21 expressions of the kind people had trouble with on the exams. I won't provide solutions because you can figure out the solution on your own. You can always just type them into Python and figure out the solution on your own. And finally, homework 1 will be out Monday, maybe even before Monday. It'll be due on Friday, March 11th, which is the Friday before spring break, I believe. And you'll recall that we have a midterm exam scheduled the Wednesday of that week as well. So it'll be midterm and then the homework will be due. I think you could enjoy the homework. Some of you are ready to program things that are bigger than just a single function. The way the homework looks is that you will be given a template for it, and it will contain the design of a system with signatures for all the functions you have to implement. So it's a collection of functions that taken together perform a function themselves. So follow the design I give you. Don't make changes to the function signatures, and that way, take them step by step. It's the kind of things like think of doing like 6 questions of the day that all interact with each other and are progressively harder. That's the way you should think of it. It is not a recipe for success if you wait to start it. Don't do that. If you wait, if you blow off the first week, you're not going to finish. And so make sure that you do it a bit at a time as soon as it comes out. All right, I promised you we'd go over the Lab 4 solutions. We didn't get a chance to do it last time, so we'll start with those. Reverse words takes a string and returns a new string that has the same words, but with the words individually reversed. So this is a test, has the same words in the same order, but each word individually is reversed. The key idea here is to take the string S and split it into words. The split method of strings so it has an optional argument which defaults to space characters, looks for space characters in the string, breaks the string up into substrings excluding those spaces, in other words, the words, and returns a list of those. And then what you can do is you can use a comprehension over that split list, reversing the individual words, collect them, and then rejoin them together. So the function looks like this. I take the string S and split it, and then every W, this returns a list. W in that W will take on successive elements of that list, which are each individual strings. W : -1 we recognize as the shorthand for reversing W. I collect those into a list, and I use join with a space to put it together. Questions? Okay, second one, isogram returns true if no character in S, apart from the space character, appears more than once in S. Otherwise, it returns false. Now, there's a lot of ways you can solve this. Some of you remove spaces and compared the length of the resulting string with the set of those characters taken from the resulting string. That's sort of the general strategy we have here. I think there was a hint that said you don't always need a comprehension. So the key idea really is to count the length of the words only, and compare with the size of the set of non-space characters. So one way of doing the first thing is to replace the spaces out and just get the string that concatenates all the words, smooshes all the words together. Another way of doing that is to use the mapping function to compute the length of every word. So in other words, I have the lowercase version of S. A lot of you forgot the lowercase. You need lowercase because it says in the instructions that case shouldn't matter. So it's usually that means you convert everything to either upper or lower. So I converted to lower. Split it apart. So this now gives me a list of the individual words all lowercase. I map the length function over that, which gives me a map structure, basically a collection of integers, the corresponding lengths of every word. I sum those guys together. That tells me the length of the words that I have. And I compare that to the length of taking the set of all the characters in the string minus the singleton set of space. So I opted to use set operations to get rid of the space. Some opted to use replaces. And it doesn't almost matter, right? Questions here? You'll notice as we get a little bit more proficient with the elements of Python, there's going to be more and more ways to do these problems. So more and more I'm going to be asking you on the questions of the day or in the labs, use this construct to solve the problem. And I do that because I want you to practice all the constructs, not just get into the habit of always using the same thing. Okay, neighbor S1, S2 takes two sequences and returns true if and only if the two sequences differ in only one element. Upper and lowercase versions are considered the same. It also tells you use a comprehension. So this becomes a lot easier because I've told you that the two lengths are the same. Not a lot easier, a little bit easier. If you didn't know that, you would first have to test the length of the strings to make, or the sequences to make sure they were same. And if they weren't the same, you would want to return false, right? So we'll get to that in a minute. So the idea here is that we're going to scan through both of these sequences together, in lockstep, and we're going to make individual comparisons. And every time the comparison returns false, meaning that there's a difference, I'm going to collect something. So I've got a comprehension in here, right in there, that lets I range up to the length of S1. So I will be an integer starting at 0 and going up to the length of S1 minus 1. So think of it as an index into the string. So I'm going to let I range over the length of S1, which is, by the way, the same as the length of S2. I'm going to compare the lowercase version of the character at position I in S1 with the lowercase version of the character at position I in S2. If they are not the same, I'm going to collect something. I don't care what it is. I happen to collect true. The only thing I'm really interested here is if this collection, this list that results, is exactly of length 1, then I know that they differ in exactly one position. So that's the trick. Collect something when the condition is met, and then when you're done, you find out how many times you met that condition. Now, this is probably not the best use of a comprehension. If I hadn't told you to use a comprehension, I probably wouldn't have used a comprehension either. Why not? Well, we did talk, I think, did we talk about when to use for and while in comprehensions, or is that today? I don't remember. We sort of did. Maybe it's today. The point here is, I usually tell people use a comprehension when you're building new structure, right? Because a comprehension builds a list or builds a dictionary or a set or something. So if you're building new structure that you want to keep or you want to use, then use that comprehension. Here, this comprehension builds a list and then immediately throws it away. Right? Measures the length and then throws it away. That seems counterintuitive. So normally here I would use the standard for construct to do something like this, because I'm not returning the new structure I built. And even though I am required to scan the entire list, or usually required, right? I might find that difference only in the last position. Okay, so that's the gist of this one, but it can be done with the comprehension, and it's good practice. Okay, question day 7. How many of you thought this was hard today? So I had a lot of postings on Piazza, surprising number, and they were all very much the same, actually. So first attempt, when I get a problem like this, the first thing I do is I forget the filtering function. I mean, obviously it says use a comprehension. I'm going to do some filtering. It tells you it's a filter function. That means there's probably an if involved, right? There's some condition I have to meet. But forget all that. Just get the iteration right first. So I'm going to start with filter words S, C1, C2, and all I'm going to do is return a list of what I want to iterate over. So here I'm going to create a new list, W for W and S, again lowercase, again split. This should return a list of the words in S. And I then go and test that. Here's to be or not to be. I have to provide these arguments, but I in fact get back to be or not to be. So that seems to work fine. So develop these things incrementally. Start with the basic part. Get it right. Check it. Make sure it's doing what you expect it to do. And then the next step is, let's just keep the words that have character 1 in them. So I'm going to extend my previous definition with this filtering condition that says if C1 and W. So this is a character. C1 is a character. W we know is a word because we've just seen the collection of W's. So this is an easy extension that I can test, and I see that the character O in these words appears in these 4 words. And I can check it. Looks right. So now the easy extension then is to incorporate C2. How do I do that? Well, I use this Boolean, this if returns a Boolean. This is a Boolean, true or false. I need another Boolean, and I'm going to use and to connect them. C1 and W and C2 and W. And then I can test that, and it works. So the insight here, and this is important, as things get more complicated, develop incrementally, test as you go. Don't expect to sit down and write out the solution in its full form on the first try. If you do that and it doesn't work, you have a messy debugging problem because you don't know where you made a mistake or why it doesn't work. And there's 20 examples of that on Piazza. If you look at the Piazza questions, I realize many of these are private. Almost all of them struggle with the same thing. Almost all of them try to write out the thing and then say, it doesn't work, I don't understand why. Where's my problem? If you had developed it incrementally, if this didn't work, you would know that your problem was exactly here because the previous incarnation worked. And so it helps you, by doing this series of modifications, it helps you develop in a way that you can catch the bug early when it's still clearer to you. And you know, I'm telling you this, you're all sitting there going, yeah, I get it, that makes sense, sure. You're not going to do it. You're going to try to write the solution first time, and it's going to cost you. And only when you fail enough will you realize that, yeah, I probably should do it incrementally. But take it from me, start now, do it incrementally, you'll be much better off. What about the optional condition? I'd mentioned in the question they hand out, says, what if I don't give you a C2? Turns out you don't have to do anything. The reason you don't have to do anything to make it work is because I stupidly, I included the thing I was asking you to include was in the template function. So I developed a solution first, converted to a template, and I forgot to remove the optional argument in the signature. So I've been using this signature here. This is not the signature you had, right? So the signature you had was this one that had an optional default argument for C2. And so C2, if I don't provide it, it will not give me an error because it has this default value. Remember we did fancy definitions a while ago? This is an example of when it works. And so C2 will default to this empty string if you don't provide an invocation. But the reason I asked you this optional add-on thing is I wanted you to think about why this works. The reason this works is if C2 is the empty string is a subsequence of every other string, including itself. So if C2 is not provided, this becomes empty string in W, which will always be true. For any string W, this will be true. So even for the empty string, even if W were officially the empty string, which wouldn't happen because of the comprehension, it would still be true. So this is a special property of strings, not of all sequences. The empty list is not in the list, but the empty string is in the string. So it's a special property of strings among all sequence types, only because in a string, every element of that sequence is of the same type as the sequence itself. We know that's not the case for lists. In a list, an element might be an integer or a floating point or itself a list. It is not the case that every element of a list is itself a list. It might be the case, but it's not guaranteed. For a string, every element of a string can only be a character and can only therefore be a string. So this is a good example of what a default value gives you the added functionality you want. And by the way, I would remember this because it's the kind of thing that becomes interesting on an exam. Write a function that works for strings but not for other sequences. So pay attention to this. It's important. So where did I see you guys struggle? This is from the Piazza notes. So most of the problem was with that filter condition. Remember that the filter condition is introduced by an if. So the things that follow the word if, the word while, right? The word else if, those things are evaluated in what's called a Boolean context. In other words, if you say if something, that something is going to be treated as if it were a Boolean. The only thing if cares about is whether its condition is true or false. The only thing while cares about is if its condition is true or false. That means whatever you put there is going to be looked at as by Python, not as a character, not as a sequence, not as a range, not as a map function. It's going to look at it and say, is this true or false? It's the only question it asks. We say that's evaluating in a Boolean context means we only care about the truth value of that thing. So expressions evaluated in Boolean context don't necessarily have to be Boolean. So this is the thing that most people asked about. They had this condition, looks right, but C1 and C2 and W is not what you think it is. This thing here is only going to be considered in Boolean terms. Is it true or is it false? So arbitrary expressions, when converted to Boolean, so if we take a number and convert it to Boolean, it's almost always going to be true. That stands for a string, a C, anything you can come up with will almost certainly be true. The only exceptions are empty sequences or collections. So the empty list is false. Empty tuples are false. Empty strings are false. Empty ranges are false. Zeros are false. The zero integer, zero float, zero complex, they're all false. But any other number is considered true. And finally, the constants, none and false, are both false. Well, false is obviously false. Right? False is false. None, surprisingly, is considered false. So these interpretations, so I've heard people say, well, these are falsish or falsy. And the things that evaluate to true, like the number 15, is truthish or truthy. It doesn't matter. Call it what you want. In a Boolean context, when you're interested in whether it's true or false, all of these things have logical interpretations. So what does that mean? If you write this expression here, this comprehension, what you're really saying is if C1 and C2 and W. Because the AND binds looser than the in the order of operation. So this expression here in a Boolean context is this true and is this true? Well, here's the rub. everything in C1, anything in C1, with the exception of the empty string, is going to be true. So this becomes if true and C2 and W. So as long as C1 is not the empty list or the empty string, this expression resorts to a condition on C2 only. So I would get messages on Piazza saying, I tried this and it ignores C1. So some people would exchange them and do C2 and C1, and now it ignored C2. And the answer is yes, because you're thinking that you're interpreting this as C1 and C2 both in W. But that's not Python. It's not Python, right? Expressions have a unique and unambiguous interpretation in Python. It may not match what you think of loosely as your interpretation, but it is well formed and it is rigorously defined. This is why I gave you expressions to practice today and why those were on the exam. Everybody can make this kind of mistake. It happens. But you will make this less if you practice your expressions and really think about the order of expressions. So here there were two problems. One is this kind of wacky interpretation of C1 and C2 both being in W. And that comes not from the truthish interpretation of non-Booleans, but it comes from not remembering that the order of operation is that in is tighter than not, is tighter than and, is tighter than or. So you remember this? Forget what lecture it was from, February 7th or something. Or is the loosest binding, then and, then not. All of the logical operations are last. That means that set membership and everything else binds more tightly than any of those logical operations. So your kind of loose interpretation, this kind of loose interpretation of this being, C1 and C2 in W, that's just wrong, because and is a logical operation. It's last. The only thing that comes after and are other logical operations, in particular or. So review these order of operations. When in doubt, use those parentheses. If you had tried to parenthesize C1 and C2 in W, you probably would have realized your mistake. Okay? Does everybody get this? So devil's in the details with expressions. All right. Let's go on then. So we were working on iteration, for and while, and we were talking about how they relate to comprehensions and mapping functions. So here's an example, right? A function returns only words in all caps from some input. So here's my string. These three words are all caps. I want it to perform like that. Here is my for interpretation. Because I'm using a for loop, I'm going to iterate W over the split of S. I'm going to take this and break it up into a list of words, just like we did in a comprehension. I'm going to test if W is uppercase. And if it is, I'm going to append W to a list that I created just for that purpose. So I'm going to create a temporary list, and I'm going to use it to collect the things that match the criteria. And at the end of the day, I'm going to return that list. Now, this is a very commonly occurring pattern. We have these things in coding that are called design patterns or idioms. This is a common pattern. It's called an accumulation pattern. It says, I'm going to build an empty structure. I'm going to iterate over something, and when the condition is right, I'm going to accumulate that answer and then return it. Now, this is perfectly fine code. I dare say it's the kind of code many of you would like to write in this class. Unfortunately, wouldn't you rather read that? I mean, comprehensions are built for accumulation patterns. That's exactly what they're good for. So when I see this kind of coding, and I'm not one to sit here and count lines of code or anything, but to me, this takes up a lot of useless real estate. This is concise, it's specific. Somebody who's well-versed in Python looks at this, sees a list comprehension, and says, oh, they're building a list. What's in the list? Well, I can see right there. It's all the uppercase elements. Something like this, when you're a practiced Python programmer, becomes very natural. Those who write this will always just be Java coders trying to write Python. Sorry, but it's true. All right? So there's a Pythonic way of doing things that is concise, it's elegant, and it's simple. And you have to sort of, if you're going to be a good Python programmer, you have to learn those things. What about this function? This function returns a list of all of the interpretations of my name that lop off successively characters from the outside moving in. It's again a collection pattern. Here's what it looks like with a loop. Because I don't want to index Alberto like this, what I'm going to do is I'm going to use a while loop here. Again, I set up my collector. While the length of S is greater than 0, I'm going to include S. I'm going to concatenate it to L. Now, in my previous example, I think I used a pen. Again, in Python and many languages, there's many ways to add elements to a list. Here, I'm going to actually create a new list S and concatenate it to the old list and reassign to L. And then I'm going to take S and I'm going to trim away the two characters. So I'm going to eat away at it from the outside. All right? And then I'm going to go around in the loop over and over and over again while S has something in it. That works. It's harder with for than it is with while. Why? Because with for, what I'd have to do is I'd have to have some sort of index into that string and then index from both sides inwards until the two indices meet in the middle or cross each other. That's a little weird. I'd have to condition it on the length of the string and so on. This is much more elegant. Just trim away. So we also know that because of this termination of this change every time through, S, which has to be finitely large to start, will eventually go to 0. So I know this will terminate. I just don't have to figure out in advance when it will terminate. But also consider in the case of a comprehension, I can simply take that inner slice as I ranges up to the half of the length of S. So there's always multiple ways to do this. Some seem more natural than others. I actually like this while to me makes sense, as does the comprehension, mostly because I'm building new structure. And again, there's always that one bugaboo. Length of S minus I is not the same as minus I when I is 0, so be careful. All right, so this is the slide I thought we had gone over, but I guess we hadn't. So you're given an assignment. How do you decide which form of iteration? Your choices are mapping functions, comprehensions, while, and for. All right, so you have 4 essential mechanisms. The first rule is if you're constructing some new sequence structure or collection, by collection I mean things like sets or dictionaries. By sequence structure I typically mean tuples, strings, or lists. Use a comprehension. Notice that there is no string comprehension, but you can use a list comprehension with the string join method to create the string, as we've done in the examples we looked at today. So if you're collecting something that you're going to use, that you're going to return, that you're going to keep around, that you're going to use as an index, or whatever you're going to use it for, use a comprehension. If you're not constructing new structure, if you're just, say, looking through a list to find out if my name is in it, and if you don't know a priori how long that thing that you're iterating over is going to be, use a while. The while to me says unbounded iteration. Imagine that you're iterating over a list that may change as you're working on it. It may get longer, it may get shorter. Use a while so it can dynamically adjust to the changes in the list. If you can say a priori that you need this many iterations, or an iteration that is, based on the size of a list or something, if it's something that you can determine ahead of time, I'm going to have to check every student in this class to find out whose middle name is Joe. How many Joes are in this class, middle names? I have to iterate over all of you. I know exactly how many you are. Then that sort of tells me use for. Notice that I'm not collecting all your middle names. That would be a comprehension. But if I'm just looking to count how many people have Joe as a middle name in the class, to me that screams 4. Now these aren't hard and fast rules, but they're pretty good guidance. Oh, I don't actually have the last one here. I should add that. When do I use map then? Well, the answer to that is you often don't, right? Whatever you do with map, you can also do with a comprehension. The distinction between map and comprehension is that map maps a fixed function of one argument over all the elements of a sequence or collection. A comprehension can map a fixed function of one argument, but can also map other things across the same thing. So there isn't a big advantage to using map over a comprehension. But map is short and concise and simple, so if I'm converting every element of a string to a digit, I might well use map of string over the elements of that sequence. Okay. So let's talk a little bit more about this accumulation pattern. So imagine that Python didn't have a sum. Well, no sum. Sum is one of the mapping functions. Sum of a list that contains numbers gives you the addition of all the numbers in that list and returns that number. So here is an example of sum written in Python using a for loop. It starts with a result variable set to 0. And for every x in that list, I'm going to add x to the result, and I'm going to return a result. Now, this function is exactly like the other for loop we looked at before, where I had a list that starts as the empty list, and I returned the accumulated list. In the other case, I told you that a comprehension was better. If I'm collecting elements in a new list, use a comprehension. But here, I'm not creating a new list. I'm essentially adding up values, and I'm returning a single number. So a comprehension here could be used, as could a mapping function, but a comprehension would build up the list and then sum it together and throw it away, which seems a little bit less direct, right? If I'm just going to add numbers, step over the whole sequence and add them together and return the sum. So this is an example of an accumulation pattern where we're not accumulating a sequence, but we're accumulating values. So this result that where we're accumulating our answer is very much like the list where we were collecting our answer in the previous for. So this is a design pattern. It's sort of the numeric version of the collector pattern. So if I'm collecting elements in a list, it's a collector. If I'm accumulating values, it's an accumulator. By the way, the accumulator is also the name of a register in a computer design where you basically do arithmetic operations and accumulate the result. It's exactly the same idea. So these are examples of where I would use for. Notice one last thing about this for. Could I use while here? Sure. But to use while, I would have to sort of keep track of how far I'd gone down the list, and when I had exhausted the list, it seems a little counterintuitive. In the worst case, I would have to start with creating an iteration variable I equals 0, and then while I is less than the length of the list, accumulate the value of the ith location of the sequence. It's not as natural as the for. So this example is one where for is really quite appropriate and very natural. Let me point another thing out for you C programmers and Java programmers. Notice how for is constructed here. Many people, because you grew up with a language where you can't use element in sequence, but only integer in range, would have said for I in range length of L. And then down here it would have had to be L index I. You would have had to index every element of the list when you added it in. The Pythonic way is much more natural. It says for every element in that list, I get a name that tells me that is attached to that element, rather than a name that's attached to an index of the element. This is much more direct. Does everybody see that? You Java programmers out there, do you see the difference? Raise your hand if you do, because it's important. Yeah. Okay, I mean, it's clear, right? remember, you've been acculturated to using indices for everything. In Python, you use indices when you need them. But a lot of times you don't need them. And this is much nicer to read. Okay? All right, so it is 10:05. We have 15 minutes to start the next topic, which is another form of iteration. So you've probably heard or seen of recursion, and a lot of students struggle with recursion. We're going to talk about recursion a lot because it's a natural form of iteration, but it also can do things that iteration can't do. There are languages that have been written that use recursion for everything. You don't get for, you just get recursion. And it's a style of writing that you can sort of get used to, and it becomes very natural. So the thing to think about recursion is, yes, I can use it for iteration, but it also does other things that iteration doesn't do. And that's where people struggle. So let's take a look at our example for sum, which is the function we just looked like, and use recursion to come up with a sum function. The first thing you'll notice about the recursive solution of sum is it doesn't have that extra variable. In both of our previous examples, both in this accumulator pattern here and in this sort of collecting pattern here, we had an accumulating variable that was either collecting elements of a list or a set or something, or it was accumulating a value that we would then return. In the recursive formulation of this, we're not going to have an accumulator variable. The recursive formulation instead relies on this observation. The observation is that if I have a list of a bunch of elements, let's say they're just all integers, just for simplicity, the sum of that list is equal to x0, the first element, plus the sum of the rest of the list. Right, so I have 20 numbers. Take the first number and add it to the sum of the remaining 19, you get the sum of the 20. So the recursive formulation here takes this observation and turns it into a function definition and defines that function in terms of itself. And this is where people get weirded out. So this is a weird concept, but it's a natural concept that you see all the time. Land O'Lakes butter. The Native American woman is holding a Land O'Lakes butter container that has a copy of the Indian American woman holding a Land O'Lakes butter container, and on down the rat hole. These kinds of pictures. Royal baking powder, same idea. You should search for recursion. If you search for recursion, it says, did you mean recursion? It's a Google joke. It was anyway. I don't know if it still works. So these are examples of things that are self-referential. And if you remember, those of you, has anybody read Hofstadter's book, Gödel, Escher, and Bach? Anybody? When I was your age, this guy at Indiana, who's retired now, wrote a book called Gödel, Escher, and Bach. So Gödel, you know who Gödel was? Kurt Gödel, anybody? He's a mathematician around the time of the war, World War II. Escher, of course, is the artist that draws those weird pictures that sort of, you know, they distort reality. They play on the difference between 2 and 3 dimensions. And Bach, you know who that is, right? You should. This person wrote a really interesting, fun book, and it convinced a lot of people to study computer science because he, you know, it was all about art and music and math and how you compute with these things. How did we get on that? Anyway, as a kid, my mother, who was 4'11", probably 4'10" now, she's really old, she used to have to make her own clothes because when she moved to the United States, people here were much taller than people in Italy. Why? Because they had the war. They were all kind of malnourished as kids, so they didn't grow as tall. So she moves to the United States and finds out that the only place she can buy clothing is in the children's section because she's like 4'11" tall. So she started making her own clothes, and she had this cool mirror setup. She had a mirror in her bedroom with a mirror on a pole so you could see the front and back of yourself. Like you've seen it in like a clothing store. As a kid, I was fascinated at lining up the mirrors and sticking my head in the middle, and because you could see like the reflection of it was exactly this kind of thing. And I remember being just captivated by that whole idea. Perhaps that's why I was fascinated by recursion when I first encountered it. But it is this kind of weird thing that seems kind of magical. Let's take a look at a recursive function. So the idea behind recursion is I'm going to solve a bigger problem by solving a smaller version of the same problem, and then accumulating the answers of those smaller versions to get a bigger one. So here's my first attempt at a recursive function for sum L. It says if L is the empty list, return 0. Otherwise, return the value of the first element in the list added to the sum of the remaining elements. This is exactly what I showed you in that formulation. Add the first element to the rest of the elements. The only thing that's missing is if the list is empty, meaning there's nothing there, then the value there is 0. The value of a collection of empty numbers summed together is 0. So the smaller problem here, this problem, is just one element smaller than this problem when it's invoked. And notice that in this definition, I have an invocation of the function that I'm defining. And that's what weirds people out. How can you define something in terms of something that hasn't been defined yet? So let's take a look at how this operates given an invocation of that value. Here's sum of 1, 2, 3, 4, which I'll help you sort of cut to the chase. This is going to be 10. We're going to get to 10. So I'm going to use this little arrow in to mean that I'm entering the function with this value. So I'm invoking sum 1, 2, 3, 4. So 1, 2, 3, 4 will be mapped to L. L is not the empty list, so I will return 1 plus the sum of L on the remainder. So within the evaluation of sum 1, 2, 3, 4, I'm asked to evaluate sum 2, 3, 4. So now I suspend the execution of this while I compute the value sum of the remaining list. I invoke sum again. Now 2, 3, 4 is mapped to L. It is not the empty list. So I'm going to return 2 plus the sum of 3, 4. So I suspend execution of that function and go and evaluate the sum of 3 and 4. L is mapped to 3, 4. L is not empty, so I am going to add 3 to the sum of the list 4. So I suspend execution of sum and I re-invoke it with the sum of the one element list 4. Now L is the one element list 4. It's not the empty list, so I will add 4 to the sum of the remainder of the list, which is finally the empty list. So this invocation of sum will not get to this return. It will get to this return and return 0 because L is the empty list. So I will now show the exit value is 0. And that 0 is combined with the 4 that I left suspended in the last invocation, 4 plus the sum of the empty list, and that will now return a 4, which is added to the 3 I left suspended in the previous invocation. I now know that 3 plus the sum of the list 4 is 4, so that's 7, and I get a 7 back, which is returned in the previous suspension where I had a 2 plus the sum of the list 3, 4, and that's 7 plus 2 is 9. And then I get all the way back to the first invocation. I had a 1 plus the sum of the list 2, 3, 4, which is 10. So I compute as I enter the function. I keep calling myself until eventually I hit a condition where I can start exiting. And as I unwind this recursive calling of myself, I do some work, which is this addition that computes the final result. Now, this is a very special form of recursion called tail recursion. It is exactly equivalent to iteration. And in fact, if you write tail recursive functions, the language compiler will often recognize it as such and rewrite it as iteration. But conceptually, mathematically, this is a lot cleaner. Right? It just says to solve the big problem, solve the smaller problem, and then manipulate that result. So we'll notice that one invocation in particular was a little bit different than the other ones. And that invocation was when this empty list was passed, I used this return statement rather than this one. We call this case the base case. It is the one path through my function that does not invoke itself. So if you look at this function, the structure of the function, there's an if statement. There's like two paths of execution in this function. One path happens when L is the empty list and I hit this return and exit. The other path happens in every other case when I hit this return. If both of those paths invoke sum, you're going to lose because it will never exit. You always have to have at least one pathway through your function. It isn't defined in terms of itself. And that is called the base case in the recursion. And I'm going to label it up here. I always check on entry, have I reached the base case? And if I have, what do I return? If I don't have the base case, then I have to figure out how I can compute what I need to compute in terms of calling myself. This second path through the function is called the recursive step because it involves a recursive invocation of myself. So as you structure your recursive functions, look to organize the base case and the recursive step. You always have to have at least one of each of those. If you don't have a recursive step, it's not a recursive function. And if you don't have a base case, it's not a function you want to write because it isn't going to ever terminate. Now that base case may be a null pathway. It may not return anything. It may just be something where it evaluates false and the function terminates and returns nothing. That's okay, but there has to be a way out and through that function that does not involve calling itself. So the recursive step decomposes the problem until you get to a base case, and then you recompose the solution. This is the schema you should have in your head for how a recursive function works in the simplest case. There are lots of examples. Sum is a simple one, but there are many, many examples. Let's look at another one, factorial. Recall that n factorial is n times n minus 1 times n minus 2 all the way down to times 1. It's also the case that I can reformulate n factorial as n times n minus 1 factorial. In other words, this part of the problem is still a factorial, but just one smaller. It's exactly analogous to sum, except I'm multiplying. So here's an example of a factorial definition. It checks to see if n is 0, because the base case for a factorial is n. 0 factorial is 1 by definition. And if it's not 0, I'm going to set the result to be 1, and then for I in this range, starting with 1 inclusive up to but not including n plus 1, I'm just going to accumulate the result by multiplying I against the current result. So this is a formulation of factorial that is iterative rather than recursive. You'll notice that this whole thing here is a little bit awkward, right? Because range 1 to n plus 1, if n is 0, this will be the empty range. And so result 1 would just be returned. But it's here to make it explicit that the factorial of 0 is 1, not necessarily required. We do have a problem if the number is a negative number. We don't check that here. So this is the analogy to the iterative version of sum. I have this accumulator variable, which is result, just like I did with sum. Now let's look at the recursive formulation. Recursive formulation looks just like sum. I have a base case that returns 1 this time, because that's the multiplicative identity. And otherwise, I have n times the factorial of 1 less than n. So this is my base case. This is my recursive step. It looks exactly the same as sum. Now, one of the important design considerations in a recursive function is that for every recursive step, when you invoke yourself, you need to invoke yourself in a way that approaches a base case. So let's just examine what that means. Let's say I change this function instead of n times factorial n minus 1, it would be n times factorial n plus 1. What would happen? For any positive n, what would happen to this invocation? Anybody? Go ahead. It would never terminate, exactly. Why? Because every time I call myself, I'm getting, in a sense, farther away from that 0 case, which is my way of kicking out of this endless recursion. I need a way to escape calling myself. When you stick your head between the mirrors, there's no escape. You need a way of going down just far enough and then getting out. And if you don't approach the base case in every factorial call, you're hosed. Okay, we'll stop here and pick up recursion on Monday. Don't forget there's a question of the day due on Monday, and watch for your you can watch for your homework one in the short term. Have a good weekend.